Well, hello, honors pre-calculus students. Mr. Hazelhorst here. First thing I want to do today is I want to share with you a bit of sad news and give you a moment to reflect and maybe mourn a little bit. You may not realize it, but today is the last day that we will cover new material in honors pre-calculus. I'm going to give you a moment to kind of compose yourselves. I know that this is going to be hard for some of you to hear. But that's just the truth. Today is the last day of new material in honors pre-calc. So I'm gonna ask for you to be tough, control your emotions, be strong for each other, and let's persevere through this together. All right, well, what we're going to talk about today are derivatives. We mentioned this a little bit yesterday as we worked with the slope of the tangent line of a function. And so today we're going to formally define the idea of a derivative, kind of work through how to solve it, which you already have a pretty good idea of what to do, and talk about what we can use that for. All right, so let's jump in with the formal definition of a derivative. So here's our formal definition of a derivative. You can see it says the derivative of f at x is given by f prime of x, which is equal to the limit as h approaches 0, and then we see our same difference quotient that we've been working with the last couple of days, provided that this limit exists. All right, so as we find the limit of the difference quotient, that is finding the derivative of the function. Okay. Now you're going to notice some new notation here. You see we have this f with kind of an apostrophe and an x. Again, that is read as f prime of x. All right, and f prime of x is the derivative of f of x. And we mentioned this yesterday. We used the derivative yesterday because the derivative is going to represent a function that is used to find the slope of the graph at the point f of x, or excuse me, x f of x. So again, as we worked with the tangent lines yesterday, we used the limit of the difference quotient to find the slope of that tangent line. And that tangent line, again, is representing the slope of the graph at that specific point. And so we're going to continue to work with that exact same function today. So if you had a pretty good grasp of what we were doing yesterday, hopefully today will fall right in line and be just as simple. So I want to work through a couple of examples. We'll find the derivatives and also kind of add on one simple new concept. I won't even call it a new concept. We're going to add on another concept today using something we've done many times before in the past. So let's pull up our first example. So in this example, we want to find the derivative of the function and then find the equation of the tangent line at the given point. So we're just taking what we did yesterday one step further. Yesterday we just found the slope of the tangent line. Today we're going to find the actual equation of the tangent line. But for the most part, our work is very, very similar. And so let's just jump right into it today. At this point, I'm hoping you already know how to find a derivative, but we want to work through that part as well. So again, we're going to find the limit as h approaches 0 of the difference quotient. So let's get that all set up here. So again, the limit, come on, pen. All right, my stylus doesn't seem to want to work. So the limit as h approaches 0. Again, I apologize for my handwriting. I'm not very good with these styluses. But we got the limit as h approaches 0, and now it's time for the difference quotient. So the first thing we need is f of x plus h. So a reminder, when we're finding f of x plus h, we're taking x plus h and plugging it in anytime we see x in the original function. So f of x plus h is going to look like this. We're going to have 3, and then I see my first x, so that's going to be x plus h, quantity squared, minus 2 times x plus h. So this part of the function is just simply representing f of x plus h. We plugged x plus h into the two places that we see f, or x in our equation. Now we need to subtract f of x, so minus 3x squared minus 2x. And we're going to divide this all by h. Now, it'd be nice if at this point we could work direct substitution, but we know if we plug 0 in for h at this point, we'll end up with an undefined function. So we can't find the derivative just quite yet. We need to simplify some things down. So let's just kind of algebraically simplify down our numerator. So I'm going to start out by working with the x plus h squared. So we know that would give us 3 times the quantity x squared plus 2x h plus h squared. And I'm going to go ahead and distribute here, so minus 2x plus h, or excuse me, plus, minus, let's go this, plus a negative 2h minus 3x squared minus 2x. So for the sake of saving room here, I'm just going to work the numerator here, and then we'll bring the limit and the denominator back in here for a moment. But I don't have a lot of space on my slide, so just kind of bear with it here. All right, so we'll go ahead and distribute the 3. So we end up with 3x squared plus 6xh plus 3h squared. Bring in the rest, minus 2x, I'm doing it again, plus a negative 2h, minus 3x squared minus 2x. Alright, so if we simplify things down here now, if we just cancel out like terms, we can see the 3x squareds, those would cancel out. I have some 2x's here, those are going to cancel out. And it looks like that is all that's going to cancel out. Now, if we look at our terms that were remaining, we see a 6xh, a 3h squared, and a negative 2h. And again, notice, what do all three of those terms have in common? They have an h in common. So let's factor that out, because again, remember, we still haven't brought the denominator back into play. We're dividing this all by h, and so those will cancel out. We'll be able to use direct substitution. Life will be good at that point. All right, let me switch back colors. So, again, we're going to factor out the h. So we'll have h times the quantity 6x plus 3h minus 2, all divided by h. And so the h's are going to cancel, and we're just simply left with the limit as h approaches 0 of the function 6x plus 3h minus 2. So if I find that limit, pretty simple here, right? Plug 0 in for h, so the 3h term cancels out, and here's our derivative, 6x minus 2. So that's our derivative of our function. So now what we want to do with this is we want to use it to find our slope. So let me change colors here so we can distinguish some things. So if we're going to find the slope of the tangent line would be equal to 6. And now if I'm going to plug in my point, my x-coordinate of my point, 3 minus 2, just like we did yesterday. So my slope at this point we can see is a positive 16, 18 minus 2. All right. Now, we're not done here. Yesterday we quit with just the slope. Today we want to find the tangent line, or the equation of the tangent line at that given point. So I'm going to switch colors again here. And so we're going to do this the simple way. If we're given the slope and we're given a point, the easiest way for us to write that equation is using the point-slope form of a line. So our equation of our tangent line will just simply be y minus 21, which is equal to the slope times x minus 3. And there is your equation of your tangent line. And now we're done. So we've got the derivative here in blue, and we have our equation of our tangent line. And we are now done. All right? So let's try one more example, and then we'll cut you loose for today. So here's our second example. Again, we want to do the exact same thing, but we're going to work with the function f of x is equal to the square root of x. So I'm going to use this example just to remind you of an important technique that we learned the other day, get a little more practice with that, but you'll see basically our work is the same. So again, we're going to find the derivative to start, set up things the exact same way. We want to find the limit as h approaches 0 of f of x plus h, which would be the square root of x plus h, minus f of x, which is the square root of x, all divided by h. All right, so at this point we need to simplify this down because, again, we can't apply direct substitution at this point. So I want you to think, all right, what have we covered in the last couple of days that could help us out here? Well, hopefully what you're thinking is the rationalizing technique that we covered earlier this week. And that is exactly what we are going to apply here. So, again, to apply the rationalizing technique, we're going to multiply top and bottom by the conjugate of the numerator. So we're going to multiply by the square root of x plus h plus the square root of x divided by the same thing down below, so square root of x plus h plus the square root of x, and simplify from there using the rationalizing technique. So again, I'm just going to show the algebra work here, and we'll bring the limit back in the end. So as we FOIL basically the numerators here, again, since they're conjugates, the product of that is going to be a difference of squares. So we're going to end up with the square root of x plus h times the square root of x plus h, which is just simply x plus h. And then minus the square root of x times the square root of x, which is just x. And this will all be divided by h times the quantity square root of x plus h plus the square root of x. And so now we can see some things happen here. The x's are going to cancel each other out, and all I'm left with in the numerator then is just an h, which would cancel out with that h in the denominator. So all we're left with at this point is the limit as h approaches 0 of 1 divided by the square root of x plus h plus the square root of x. And now we can apply a direct substitution. We can plug 0 in for h. So really all we're left with then is 1 divided by the square root of x plus the square root of x, which we can simplify down even further. This would then become 1 divided by 2 square root of x. And this again would be our derivative. So now that we have our derivative, we're ready to find our slope of our tangent line. So the slope of our tangent line, m, is going to be equal to 1 divided by 2 times the square root of x, which we're plugging in the x coordinate of our point, which is 4. So we just simply end up with 1/4 as our slope. And then to write the tangent line equation, again, very simple. Going to use the point slope form just like we did before. So y minus 2 is equal to 1/4 times x minus 4. Now I believe the answers in the back of your textbook are in slope-intercept form. So my hope is at this point you could convert that equation over pretty easily. But let's just walk through that here real quick. So if I wanted to convert that over into slope-intercept form, so I'm just going to simply distribute the 1/4 through the equation. So I'm going to get 1/4 x, and 1/4 times a negative 4 is going to give us a negative 1. Add 2 to both sides, so we end up with the equation y is equal to 1/4 x plus 1. And there would be our equation in slope-intercept form. All right? So that is the derivative, the equation of the tangent line, all pretty simple. All right? So there you have it, folks. The last day of new material here in Honors Pre-Calculus. I know, again, it's a sad day for you, but I thank you for being strong emotionally for each other, supporting each other through this day. And I'll see you on Monday. Remember, Monday we'll be reviewing for your last test over chapters 11 and 12, our three-dimensional graphing, and what we've learned here about limits in chapter 12, and we will take that test during whatever day you're scheduled to take your final in this class. So have a great weekend. Thanks for listening. And if you have any questions, this video will be posted online so you can rewatch it, or just bring those Monday and we'll take care of them then. See you guys. Bye.
Made with Doodlecast Pro.